Hello everybody. In this video we are going to be looking at the solutions to the Physics 1 Simple Harmonic Motion Practice Problems 1. Let's take a look at the first problem. A 3.0 kilogram mass is placed on a vertical spring with a spring constant of 60.0 newtons per meter. Find the expansion of its equilibrium position. So in this problem, we are given the mass of the object, which is 3.0 kilograms, and we are given the spring constant of the spring, 60.0 newtons per meter, and we are looking for the displacement from equilibrium, or x. So I know I'm going to need to use Hooke's law for this problem, and I know that in Hooke's law, the force acting on the spring is equal to the negative of the spring constant times the displacement. Now, because the spring is hung vertically, that's going to be a key thing for us. The spring is hung vertically. I know that the gravitational force acting on the mass is going to equal the mass times gravitational acceleration. And because it is vertical, I know that the force acting on the spring is going to equal the gravitational force. So I can replace mg for the force of the spring in Hooke's law. And when I do that, I am going to have negative kx is equal to mg. Now I can solve for x, and solving this for x is going to give me x equals mg divided by negative k. Can't forget that negative sign. Plug in my known values into that equation, and that will give me a displacement of negative 0.49 meters. Problem 2. What is the force constant of a Hooke's law spring if the extension of the spring is 6.0 centimeters when a mass of 2.0 kilograms is placed on it? We are given the displacement of the spring, negative 6.0 centimeters. And again, I'm making my displacement negative, so my force will be positive. Converting that to meters is going to be negative 0.060 meters. I know I have a mass of 2.0 kilograms, and I know that I am looking for the spring constant. I know the problem says force constant, but the word constant there should tell you that you're solving for K. Now I know that this spring is being hung vertically because if I'm putting a mass on the spring and it causes the spring to stretch, that tells me that the spring is vertical. So I'm going to start off with Hooke's law. And just like the last problem, I know that in Hooke's law, when it's hung vertical, the force acting on the spring is going to be equal to the force of gravity. And I know my force of gravity is equal to mass times gravitational acceleration. So if the spring force is equal to the gravitational force, then I can replace the spring force with mass times gravitational acceleration. And when I do that, just like in the previous problem, I have negative kx equals mg. In this case, though, I am solving for k, or the spring constant. So solving for k, I have k equals mg divided by negative x. Plug my known values into that equation, and that will give me a spring constant of 330 newtons per meter. Problem number 3. A geologist finds that the frequency of a pendulum is 0.3204 Hertz when at a location where the acceleration of gravity is 9.80 meters per second squared. What is the value of g at a location where the pendulum's frequency is 0.3196 Hertz? So we're given the frequency of the pendulum at the first location is 0.3204 Hertz. I am given the gravitational acceleration at the first location, 9.80 meters per second squared. I'm given the frequency of the pendulum at the second location, 0.3196 Hertz. And I'm being asked to find the gravitational acceleration at the second location. I know that I can't use frequency in my pendulum formula, But I also know that I can find the period of the pendulum from the frequency pretty easy. So to find the period of the pendulum at the first location, I simply take the reciprocal of the frequency of the pendulum at the first location. And when I do that, I will have a period of 3.1211 seconds. Notice I've carried my decimal to 4 places. And that'll be important to help me get an accurate answer to 3 significant figures later on. So now I have my period at the first location, and I know the gravitational acceleration at the first location. I can find the length of the pendulum, because remember, the one thing about the pendulum that doesn't change when I move it from the first location to the second is going to be its length. So to find the length, I know I take t squared times g and divide that by 4 pi squared. And I put my values for t and g for the first location into that formula. And I'm going to get a length of the pendulum of 2.418 meters. Now I need to find the period of the pendulum at the second location. And again, I just take the reciprocal of the frequency at the second location. When I do that, I will have a period of 3.1289 seconds. Now I know the length of the pendulum. I know the period at the second location. I can solve for g at the second location. So I'm going to solve my pendulum formula for g for the second location, and g is equal to 4 pi squared times L divided by t squared. I plug my values for the second location into that formula, and I'm going to get a value of g, or gravitational acceleration, of 9.75 meters per second squared. Problem 4. In 1851, the French physicist Jean Foucault, I probably pronounced that horribly wrong, but that's okay, hung a large iron ball on a wire about 61 meters or 200 feet long to show that the Earth rotates. The pendulum appears to swing in different directions as the Earth turns under it. Calculate the swinging frequency of this pendulum. So the length of the pendulum I know is 61 meters. I'm looking for the frequency. Once again, I can't get the frequency from my pendulum formula, but I can get the period from the pendulum formula, and from the period I can find the frequency. So using my pendulum formula to solve for the period, which it's already solved for, no rearranging necessary on this one, I just plug my values for the length of the pendulum and my gravitational acceleration of 9.8 meters per second squared into the pendulum formula, and I will get a period of 15.68 seconds. Now to find the frequency of the pendulum, I simply take the reciprocal of the period, and when the reciprocal of 15.68 seconds will give me 0.064 hertz. Problem number 5. A pendulum is 0.75 meters long and has a period of 4.17 seconds. Is this pendulum on the Earth, Moon, or Mars? Do a calculation to prove your answer. The length of my pendulum is 0.75 meters. The period of my pendulum is 4.17 seconds. So what I'm going to need to do is solve my pendulum formula for the gravitational acceleration and see if that gravitational acceleration matches the known accelerations on my 3 possible locations. So taking my pendulum formula, solving it for g will give me g is equal to 4 pi squared times L divided by t squared. I plug my values for the length and the period into that equation, and I'm going to get a period of 1.70 meters per second squared. Now you may not know the gravitational acceleration of Mars or the gravitational acceleration of the Moon by heart. You should know the gravitational acceleration on Earth by now, but you might not know the other two. You're going to probably look those up or Google them. And let's face it, you guys have plenty of free time on your hands, so I don't feel guilty about making you do that. And when you do that, you're going to realize that this pendulum, or the gravitational acceleration of this pendulum, does match the gravitational acceleration of the Moon. So your pendulum is on the Moon. And quite frankly, if you don't know what planet your pendulum is on, you're not taking very good care of your pendulums. Shame on you. Problem 6. Samira measures the period of a swing on a playground using her mobile phone. 10 periods takes 27.56 seconds. Well, what is the length of the swing's ropes? So we could treat the swing as a pendulum because we know that the swing is going to be moving in a simple harmonic motion. And if 10 swings or 10 periods take 27.56 seconds, to find the length of one period, I simply divide that by 10, and I know one period is equal to 2.756 seconds. Now I can use my pendulum formula. Solve for length. I have L equals T squared times G divided by 4 pi squared. I plug my period and my gravitational acceleration into that formula, and that will give me a period of, or I'm sorry, that will give me a length, I'm sorry for length here, that will give me a length of 1.89 meters.